the person who really did the lion's share of this work in terms of the noise measurements is Leon Chen, and we never could have done all of this on the experimental side, of course, without the wonderful materials Hawkins, who we heard from earlier today, and her postdoc, Professor Prochaska, was big on the initial stages involved in the growth of these materials. So very, very briefly, I think everyone in this room is already familiar with this, but this is a little bit pedagogical. So, what is a Fermi liquid? Well, we know what a Fermi gas is, right? If I have a bunch of non-interacting fermions and I throw them in a box and I ask what the ground state looks like, if we look at momentum space, my filled states start from k equals 0 and sort of expand outward, and it's the Pauli principle that keeps everything from falling into a single spatial state. If I do it in 3D, I get a sphere. And we understand how to think about these things. Low energy excitations of the system are particles and holes. I can take an electron out of the filled state and put it into an empty state above the Fermi energy. There's a nice crisp Fermi surface at 0 temperature between the filled states and the empty states. These excitations have charge of magnitude e. They have spin 1/2. And if you then throw something like this into a Drude picture, you artificially insert some kind of scattering. You end up with this idea that the resistivity at low temperatures is going to, even without a lattice, the resistivity at low temperatures is going to look kind of like rho naught, so residual resistivity set by the dirt, plus a term proportional to the temperature squared, and that temperature squared has to do with this argument about phase space, Pauli blocking and phase space for scattering at low temperatures. And of course, the heat capacity, we all learned this in undergrad solid state or StatMech, the heat capacity for this Fermi gas is going to go like T. Now, Landau's great intellectual triumph of the 20th century was one of his intellectual triumphs was this idea of Fermi liquid theory. So I can turn on interactions in some nice adiabatic way, and there should be a one-to-one correspondence between the non-interacting ground state and the interacting ground state. And the idea, what you end up, you still have a filled Fermi C in K space with a Fermi surface. The low energy excitations are now quasi-particles. They have a finite lifetime because the interactions between the residual interactions between the particles broaden these things out in terms of having a lifetime. But parametrically, these quasi-particles are always distinct from the Fermi surface. As you cool down, the lifetime becomes longer and longer and longer. The energy, the broadening of these states becomes less and less and less. And quasi-particles are always well-defined. And for the same kinds of arguments, you get, particularly if you're in a lattice and you're willing to throw in Umlauf scattering, you can readily see, well, it's a little subtle, that the resistivity is going to have some residual term and a t-squared term at the lowest temperatures. And there's a t to the 5 piece involving electron phonon scattering. And again, the heat capacity goes like this. So what happens when Fermi liquid theory doesn't work? The strange metals are this putative class of materials that are identified as having certain common phenomenology. And in fact, I would argue that it's a really interesting question whether an intellectually interesting question is, are all strange metals as defined this way really the same thing? Is there a real organizing principle behind this? But what you see here, and fix this slide. This is supposed to be a 1, and this is supposed to be a 2. The point is that there's a broad region of temperature versus some tuning parameter, in this case field, in this case doping, where the power law of the resistivity is wrong, right? The resistivity goes like T instead of T squared, the low temperature limit. And also there tends to be a different scattering rate for the transverse and longitudinal pieces of resistivity. There tends to be things like logarithmic corrections to the heat capacity. So, there's all kinds of exotic things that have been put forward on the theory side about involving things like ADS CFT and fairly exotic things about whether there even are well-defined quasi-particles at all in this system. The example we choose to work with is a terbium-rhodium-2 silicon-2. This is material that's been well known for 20 years, if not more. And the basic idea with this material, if you go down towards absolute 0, there's a quantum critical point between an anti-ferromagnetic state, where the terbium atoms order the f electrons order anti-ferromagnetically here, and you have kind of a small Fermi surface. Quasi-particles are kind of heavyish. And then on the other side, on the high field side, you disrupt the antiferromagnetism, and you now have kind of a large Fermi surface. And again, you have quasiparticles that are heavy. But the point is that either side of these of this critical point, the system's a Fermi liquid. But in the middle of this here, where the system in some sense doesn't know which electrons are really fully participating in the metallic state, the system is a strange matter, right? You have rho going linear in T, you have all this other phenomenology I just mentioned. And it's a very, it's an interesting question, how well defined are quasiparticles? And just for reference, all the experiments I'm going to describe to you are being done at temperatures warm enough where this quantum critical fan just spans all available magnetic field space that you can get to in the lab. So everywhere we're going to look in our measurements, we're going to look from 3 Kelvin and up. The whole region is not Fermi liquid. The whole region has rho linear in T. A thing we would like to do, of course, is to do measurements like I'm going to describe at lower temperatures, where you can try and field tune across the different regimes. That's very exciting, and I'll talk more about that. So what experiments could you do to actually see if quasiparticles exist? This is a worthwhile thing to think about. People love doing things like photo emission, but the problem with photo emission is it's kind of a brutal thing, right? You're ripping whole electrons out of the system. You could do scanning tunnel microscopy, but again, you're ripping out or dropping in whole electrons in the system, entire electrons in the system. So, is there something else you can do? And the answer I'm going to try and persuade you is that we can learn something from noise. Keep an eye on the time, I don't want to run along. So in equilibrium, if I have a conductor, there's this thing called Johnson-Nyquist noise. It's just a consequence of thermodynamics and the fluctuation dissipation theorem. There's thermal agitation of the electrons, and I end up with I can now talk about as current noise or voltage noise, depending on whether I have a short circuit or an open circuit. But the noise in here is proportional to the temperature, at least at low frequencies. The usual derivation, you can derive this very nicely, thinking about transmission line you terminate with your resistors. This is an equilibrium effect. It's always there in equilibrium. And I can give you a full derivation if you want. Actually, Nyquist's original paper is remarkably good and clean. It's like about 2.5 pages. It's really very nice. So this is white. The noise is white in frequency at the scales comparable to KT over H bar. So it's always present. You can actually use Johnson noise as Johnson-Nyquist noise as a thermometer. So here's an example where we take just a resistor and you vary the temperature and you measure the actual noise of the device and you look at it as a function of temperature. And guess what? It really does agree with what your independent thermometer says. So you can really do nice things here. Now, in non-equilibrium situations, it's generally not possible to automatically separate Johnson-Nyquist noise from other noise in the system. So what other noise am I talking about? This is the interesting noise. This is shot noise. Okay. So what is shot noise? Shot noise results just from the statistical variation in the arrival times of their electrons. So Schottky was thinking about this 105 years ago in the context of vacuum tubes. I just have electrons boiling off the filament. There's some Poissonian statistics that describe the electrons traversing my system. And so their arrivals are just a Poisson process, and you can do the math. And what you find is that there are current fluctuations because, statistically, sometimes electrons arrive more frequently in time than other times. Right? Sometimes they happen to be close together, sometimes they're far apart. On average, there's some average arrival rate. But if you compute the mean square fluctuations in the current per unit bandwidth, so we kind of Fourier transform our stuff here. So S sub I has units of amps squared per hertz, right? This is mean squared fluctuations per unit bandwidth in frequency space. You get twice the electronic charge times the average current if you just have Poisson distributed particles. Okay. So shot noise really microscopically is current noise, but in practice we measure voltage noise, so you can relate the current and the voltage via the differential resistance. And also, usually what people do is they describe the noise they actually measure in terms of something called the Fano factor. So it's the ratio of the measured current noise to 2 right? So it's how does the noise stack up to what you'd expect for independent Poissonian electrons? And you can see, in some sense, because this exists, because the charges come in little packets, this is a way of measuring the charge, right? This is often an undergrad lab experiment with a vacuum tube. You can actually go and measure that the charge of the electron is 1.6 times 10 to the minus 19 coulombs. It actually is. So if you do this in tunneling, where you're adding and removing whole charges, you can do a little bit better than this. You can first of all, there's a way to deal with the crossover between the purely equilibrium thermal noise at zero current and what's going on at finite currents. This is kind of the nice expression for Fermi-Dirac statistics, quantum factor of 1. And the low bias limit, it gives you the Johnson noise, and the high bias limit, it gives you the Poissonian result. And you can imagine a situation where you could get deviations from the Poissonian result, right? If my electrons were always paired, so I had Poissonian arrival of pairs, I would get a Fano factor of 2. If my electrons came perfectly evenly spaced in time for some reason, you can make kind of Coulomb blockade systems where the repulsion is very important, and you would get a Fano factor of 0, right? Because if the electrons truly came like clockwork, there's no fluctuations in the current. And also, if the electrons were a perfectly continuous fluid, imagine that there's no such thing as quantization charge, then I would also get a Fano factor of 0, right? If my charge wasn't lumpy, I wouldn't see any fluctuations in the current. The average current would tell me the whole story. So the thing I wanted to do was to look at a wire. The reason I want to look at noise in a wire is because it avoids this challenge of actually ripping whole electrons out of the system, right? So in a wire, you've got a constriction of some kind. It's got a lot of transmitting channels. You can approach this from a microscopic perspective, and it turns out what you should see for diffusive constriction with no electron-electron interactions is a Fano factor of 1/3. And there's actually, this is a great review article about this stuff. There's another way to think about this. Actually, you can do this from the point of view of distribution functions. So, my distribution function in my source electrode is going to be a Fermi-Dirac thing. My distribution function in my drain is going to be also a Fermi-Dirac thing, and they're going to be shifted relative to each other by some applied bias scale, right? If I cut the wire in the middle and I look in the middle, the distribution function for the electrons in the middle is going to be some linear combination of these things. It's going to have a two-step feature. And if you go through and you do the Boltzmann equation, you calculate current correlations, blah, 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 you get that the Fano factor is 1/3, right? So this is what you expect if the electrons don't trade energy with each other, but they just kind of diffuse around like pinballs in some disordered environment. Okay. So what happens if you have phonons? Well, phonons can be bad for these measurements. Phonons can basically smear things out and suppress the noise. And in fact, the one limit to think about is, imagine if the electrons talk to the phonons super, super strongly, then all you're ever going to get for the electron distribution function, even though you're trying to drive it, all you're ever going to see is something that's a Fermi-Dirac distribution at the temperature of the lattice. So you're not going to get, all you're going to see is Johnson-Nyquist noise at the lattice temperature, so you're not going to see any extra noise when you drive the system. So you can take, so this is some beautiful work that was done in sort of ordinary conventional metals in the 90s. What you expect to see as a function of how big your device is or how much time you give the electrons to talk. Like I said, here's a wire between two big fat heat sinks. The Fano factor should be 1/3. In here, if I let the electrons actually trade energy with each other, but still not talk to the lattice, the Fano factor goes up. The effective Fano factor should be √3/4, which is about 0.433. And then eventually, if my wire is really long and my electrons have a chance to talk to phonons, they cool themselves off and the noise is suppressed. Okay. So this is what's supposed to happen if I just have a kind of this was originally derived for essentially a very Fermi gas almost, like a kind of a very weakly interacting. Obviously, there have to be some interactions if this is happening, but a very weakly interacting Fermi liquid, say. That's what it was. There's no reason to think it would fail, and with stronger interactions, this is what you expect. And I'll show you. We actually go and we do measure this stuff, right? So I'll show you what we did. This has been measured before in ordinary metals, and we do it too, just to make sure we know what we're doing. So what you do experimentally is, here's your device, and you actually just look at the voltage across the device. And you digitize this as a function of time. And in fact, we do this with 2 independent amplifier chains so that you can kind of null away the amplifier noise. And you just digitize it, Fourier transform it, and cross-correlate it, and you can get the current fluctuation, the voltage fluctuations. And you can, knowing the differential resistance, you can turn that into current fluctuations. Okay. So if you go and you do this, you can make some nice progress. Okay, so what do you see? Here's what you see. All right. Here's an example of a little gold wire. It's rather narrow. It's, here it's about 600, 700 nanometers long, big, thick gold pads on either side. We made this thing at the clean room over here. And here we are at, several different temperatures. And the data points are in color with little error bars. And then the error bars are actually the standard deviation. So this actually tells you how much scatter there is when you measure repeatedly. And what you see is that the gray lines are for the Fano factor equals 1/3, and it threads the data very, very nicely. Right? So this is sort of what you'd expect if electron-electron scattering is pretty weak in the system, and it works in a very pretty way. If you go to high enough temperatures, and in fact, I've got a student where we're going to try and push this to much higher temperatures and see when it really drops off. It starts dropping off because at some point the phonons turn. Right? The interaction with phonons becomes more important as you get warmer. But even going up to 20K, the Fano factor is pretty close to 1/3. Okay. So what happens if you actually do this in the strange metal? What makes this possible is the fact that we actually can pattern wires out of the strange metal, and we can do that because we have these lovely epitaxial films that the Pashi grow. These are epitaxially nice. They're grown on germanium, which at low temperatures is nice and boring and insulating. And like I said, in our temperature range, the non-turbulent liquid regime extends across all available field space that you can get to in the lab. Okay. A key component of this was my student figuring out how to make wires out of this stuff without ruining the material. This is a hard thing in general. A lot of these correlated systems are chemically rather complicated, and the kind of processing that lets you make nice structures out of silicon or gallium arsenide and stuff can really screw up the properties of these correlated materials. The cuprates are like offender number 1 in this category. Anyway, there's a way of patterning, and I can talk about it if you want. There's a way of nicely patterning a wire out of this material and having big pads on either side of it to be well heat sunk. So here's an example of the device. You can see this is where the wires used to be attached. If you zoom in, here's the terbium rhodium 2 silicon 2 wire between 2 big thick pads. The edges look a little bit ugly. What I want you to take away from this is the key here is we're comparing resistance versus temperature for the unpatterned film and the nanowire device, and they basically fall on top of each other. These have been normalized to take care of the fact that the residual resistance actually does go up when you pattern the film because you're basically making the thing more disordered. But if you normalize things at say 100 Kelvin and look, they really are on top of each other at low temperatures. They really do look linear in T. This dashed line is sort of your guide to the eye. And then again, even the magnetoresistance, if I apply a magnetic field in plane, pointing this way, you see that the unpatterned film and the patterned wire have very, very similar magnetoresistances. So this tells you that by making the wire, you have not screwed up. You have not destroyed the material. I can tell you we tried other ways to make the wires, and this doesn't work. So this is the happy way to make wires. All right, so here's the big shot, right? This is the meat of this whole thing. Here is the remember it's terbium 2 silicon 2. People have studied this. It's a strange metal, linear in T resistivity. Quantum critical charge fluctuations is seen by things like terahertz, optical conductivity measurements. There's every reason to believe in all the measurements other people have done in the system that electron-electron interactions are really strong. So if electron-electron interactions are really strong and phonons aren't really important, which is what all the other measurements imply, you would expect to see, conventionally, if it was a Fermi liquid, you'd expect to see √3/4 as your Fano factor. You do not. If anything, so this thing is very, very quiet. What you see is the Fano factor is practically speaking 0, almost 0 by the time you get to 10 Kelvin. And it's still quite suppressed by the time you're down to 3 Kelvin, though it does seem to be coming up a little bit as you cool. Okay. And we've done this in multiple devices made from multiple films. We've swept magnetic field. Magnetic field does change the resistance because there's this magnetoresistance, but once you account for that, it doesn't change the noise at all. That data is all in the SI for the paper. So maybe it's phonons. Maybe somehow phonons are suppressing the noise, because I told you that's a possibility, right? Within the Fermi liquid treatment, it's possible to model phonons, right? What you can do is you can say, this implicitly assumes the of Franz, but you can basically say, okay, I'm going to let the electrons trade energy with each other, and they're going to thermally conduct heat out the ends of the wire, and I'm going to let them lose energy. There's some local electronic temperature, and I'm going to let them lose energy to the phonons, right? And let's assume the phonons are cold. So you can model this thing. This all works nicely, basically. You can, if you basically take a very long wire where you know that phonons are going to be important, you can do a series of measurements and try and back out what gamma, this electron phonon energy loss coefficient, you can back out what that gamma number is for your material, right? So, so what's going on is if gamma is 0, the electrons talk to each other and they trade energy, and there's an effectively heated electronic distribution in the middle. And this is the kind of thing that gives you the √3/4 phonon factor. And if you crank up the phonons, you can squish down the electronic distribution in the middle. Bottom line, if you do this measurement in gold, this has been, again, been done by multiple other groups, and we did it too, just to confirm. This number gamma is around 5 × 10⁹ in these SI units. Okay, so that's just, I have no intuition for this, but that's what the number is. You can worry about the linear T resistivity. It ends up being a very tiny correction to all of this. Please, we do the same thing in our strange metal case. So here's the data, right? Here's the wire. Here's a 30 micron long wire, also very narrow, of a terbium to silicon tube between contacts. The data points are on here, and this is basically the noise in this long wire versus bias current. And we can interpret it through that model I just showed you. And the only fit parameter for these 3 curves is gamma, right? So you know everything. The only adjustable parameter you have is this the electron phonon energy loss coefficient. And when you do this analysis, you find that gamma it's a bit bigger than for gold, right? It's a little less than it's a little less than twice as big as for gold. And so, okay, so is that enough to explain the noise suppression? No. If you wanted to squish the noise down, so if you did that model and you decided what the heck gamma would I need to really squish the noise way, way, way down, it would have to be 68 times higher than the value we see in gold, which is just not easy. Like, this is just kind of an unphysical number. And the Debye temperature stuff is even twice, is more than twice what you see in gold. So basically, there's no reason to think phonons are doing anything interesting. 2 minutes. Yeah. You might worry that maybe my device is a little bit non-ohmic. Does that matter? The short answer, no. I mean, you can basically, the noise is robustly small. If you try and correct for the non-ohmicness of the device, all it does is affect your curve fits. It doesn't affect the magnitude of the noise at all. It just affects what F you pull out, right? Bottom line, if you try and correct for non-ohmicness, all it does is make the phonon factors you pull out even lower. Okay, so the noise is really, these wires are quiet. Is there a reason to think that this is just some funny Fermi liquid thing where, okay, we have much stronger interactions than are usually considered? So even though I would tell you that phenomenologically this is in the non-Fermi liquid regime, you could ask yourself, what if it was just a Fermi liquid? You carry this through, and again, this is the people in this room have done this. This is working with Qingyan. Bottom line, what you expect is that the strongly correlated Fermi liquid should still have, where the quasi-particle weight is suppressed but not all the way to 0, you should still get √3/4 from the quantum factor. So, what does this mean? I think it's tempting to say that this implies that the quasi-particle picture, this idea that the current through this device is being delivered by discrete lumps that you can readily identify as propagating quasi-particles, maybe that just doesn't work, right? Maybe the dramatic pronouncements that quasi-particles don't really exist in the system is experimentally consistent with what I'm saying. Now you have to be careful, right? You would only get the noise to be, in this thought experiment. Having the noise be truly zero would imply that there's like no dispersive anything left over that would sharpen up as you cool down. Let me just point out there's been some progress on this. So Sudhir Sachdev's group, for example, has been trying to think about ways to calculate shot noise in strange metals. I need to reread this about 3 or 4 more times. I'm still not sure I really understand it. I will say that this paper predicts a Fano factor of the 6th, but it doesn't really predict much in the way of temperature dependence. Like it should be a 6th all the time, which is not what we see. Anyway, here's just the very last thing, just to point out something strange, something weird, okay? We mentioned this in the paper because one of the referees really wanted us to mention this in the paper. It had been in the SI. So there's a theory work that was done back in 2012 on a quantum critical system that has completely nothing to do microscopically with our system. It's a superconductor insulator transition problem. But the bottom line is they do some ADS CFT thing. They map the shot noise to Hawking radiation in a black hole kind of scenario. And the weird thing here is that, so they come up with a formula. And the bizarre thing is our data can fit by this extraordinarily well, actually. I truly don't understand why this should work. What you'd really like to do to unambiguously test this is to go up to much higher currents, but then you run into other problems. So anyway, it's intriguing. So I'll just put up my conclusions. There's lots more to do, and I'm happy to take questions.